This video is about how to solve linear equations using the addition property of equality. We'll begin with an introductory definition, which is that an equation is linear if it can be written as ax plus b equals c, where a, b, and c are real numbers and a is not 0. So real numbers just means a, b, and c will typically show up as numbers, not as the letters a, b, and c. But x is the variable in this equation, and notice that it's a single power of x. It's just x to the first. That's part of the definition as well. So let's first of all work on this definition by deciding, are these linear? We have some examples of some equations here we'll work through. The first is x minus 15 equals 20. And you'll notice here that the x variable is a single power of it. There's nothing else going on with it. And if you actually force a 1 in front of the x, which would be there but not necessarily written, then this does actually kind of fit the definition above as ax plus b equals c. Of course, it's a minus 15 instead of a plus, but the point is b is a real number, so it could be a plus minus 15 or a plus negative 15. Okay, the point is there's a single power of x. This does fit the definition, so we'll say yes for linear. Our second example reads x squared minus 15 equals 2. Well, you'll notice here pretty quickly that since the x has a power of 2, being x squared, this does not fit the linear definition, and so we'll have to say no for that one. For the third example, we have square root of 3 times x plus pi equals 0.6, and there's a line over the 6. This one has some special looking numbers in it, but it actually does still fit the definition of linear. There's a single x, a single power of x, and these other numbers are just, fancy looking real numbers. Square root, a pi is a real number, a special one. And then 0.6 with a line over it means 0.6 repeating, but again, that's still a real number. So this actually does qualify. We'll say yes, that's a linear equation. And then fourthly, we have open absolute value x plus 5 close absolute value equals 8. Okay, now this one has a simple x to the first power inside the absolute value symbols, but because of these absolute value symbols being there, we would have to say no, this does not qualify as linear. It doesn't fit the strict definition we have above, which does not have absolute value symbols in it. Now let's work on some examples where we solve linear equations, and to do so we're going to use what was said above in our title as the addition property of equality. It could mean addition or subtraction, as we'll see, but the point is that property allows us to add something to both sides of an equation without it ruining the fact that it's an equation. So our first example reads 18 plus z equals 14. And to solve an equation in general, we want to get the variable alone. You'll notice the variable in this equation is z, but it's not alone. There's this 18 that's on the same side with it, being added with it, a positive 18. So to get rid of that 18, what we can do is subtract it, which is like the opposite of the operation. So if you subtract 18, those will disappear or cancel each other out. But the issue with this property of equality is that whatever you do to one side of an equation, you must do to the other. So I'll also have to subtract 18 from the right side of this equation. When doing this, of course, the 18 minus 18 on the left side cancel out. That's the whole point, leaving us only with the z over there. And then on the right side, we'll have the arithmetic of 14 minus 18, which would be a negative 4. And that's where we'll stop. Notice the variable is now alone, so that's our answer. Moving on to a second example, this one starts as x plus 7/8 equals 9/8. So again, we want the variable alone, and to get it alone, we'll have to take away or subtract this fraction which is currently being added along with the x on the left side. If I subtract 7/8 on the left side to get rid of it, I'll also have to subtract 7/8 on the right side. Then after doing this, the x will be alone on the left side because the 7/8 minus 7/8 will have canceled out. And then we'll have the x equal to, on the right side, we'll have 9/8 minus 7/8, which is really 2/8, which I'll write it that way at first. but that should be reduced. So let's say x equals 2/8, which really equals 1/4, which would be our final answer. Let's try another example. This one is going to skip ahead now with some more steps involved. And the original example reads 7x plus 3 equals 6, open parenthesis, x minus 1, close parenthesis, plus 9. Now, when it involves more terms and more steps, I like to refer to some strategy steps that are very helpful for staying organized in a problem like this. And this simple list of steps can really simplify the process of doing a more complicated problem. As step one, we're going to distribute first. So anytime you have an opportunity to distribute something, as we do in this problem, we're going to do that first. Of course, some problems don't involve the distributive property, like the first examples we just did, and so you would even just skip that step. But since we do have the opportunity to do that, we're going to distribute the 6 into the parentheses that follow it, as we've done before in other contexts. Secondly, after doing that, we're going to combine like terms on each side. Alright, so let's get there by first distributing the 6 and recopying everything else in the process. So I'm just going to recopy the 7x plus 3 that we have here on the left side. And then on the right side, when we distribute the 6, we'll have 6x minus 6 and then a plus 9. So we should now combine like terms on each side. That's our step 2 here for doing a more complex equation. You'll notice on the left side, being 7x plus 3, there are no like terms to combine, so we'll just copy it as it is, 7x plus 3, nothing to do there. However, on the right side, we do have a pair of like terms. There are these numeric terms, the minus 6 and the plus 9. So we'll copy the 6x down, but then combine those numeric terms. A minus 6 plus 9 would be a plus 3 when combined, and that takes care of combining like terms on each side. Once we do that, which again doesn't happen in every problem out there, but in this case it did, so we made sure to do that step. The next and last step would be maybe the most important. I like to say it this way. We want to move the variables first. Okay, so now notice that the equation we have left standing here, we have a variable term on each side and a non-variable term on each side. We're going to go variables first, which, by the way, is not the only way to do this, but it's the most convenient way, as you'll see by the end here, because then we're going to go smaller to larger. And that's how we decide what to move where, out of the many possible options. So you're going to have to be disciplined to follow these steps. It will eventually, or in the end, save you time, I promise, but it may not be the natural way you would look at a problem like this. So we're going to be disciplined to stick to this. It will pay off in the end. Variables first means I'm going to look only at the variable terms. So here I have a 7x on the left and a 6x on the right. So only look at those. Forget the plus 3's that you see for a second. And I want to move the smaller one to the larger one. Well, out of 7x and 6x, obviously 6 is smaller than 7. So I move that one, and when I say move it, we're going to subtract it. We're going to do the operation that would undo or get rid of it. Well, if I subtract 6x on the right side, I must do the exact same thing on the left. So there we go, we're subtracting 6x from both sides. That's all I'm doing in this step. The result will be, on the left we have the 7x minus 6x, which would be just a single x, but then we still have that plus 3 over there, equals. On the right side, now the 6x's cancel, that's the whole reason we did that, but then we still have the positive 3 over there. Now, finally, we can get the x alone with just one quick step, which is we'll go ahead and subtract 3 from both sides, and these 3's on the left side would cancel, leaving us only with an x over there, equal to, on the right side we have 3 minus 3, which is 0, so x equals 0 will be our final solution. Let's now try another example, but where it involves starting with some verbal description. This one reads, the difference between 3 and 2/7 of a number is 5/7 of what number? Find the number. Sorry, 5/7 of that number. Find the number. Well, we're going to translate this from words to symbols, as we've done in the past, but then this one's going to result in an equation that we'll also have to solve. When we see difference between, Okay, so that's a key phrase indicating subtraction. Whenever you see that phrase difference between, it's about to show you or tell you the subtraction, which you can put in parentheses or grouping symbols. So when we see difference between 3 and 2/7 of a number, that phrase following the difference between is what's in parentheses. That's how we know what to subtract. When we say a number, we could call that x, as in our variable. And so we can write this out as 3 minus 2/7 x. That would be the difference between 3 and 2/7 of a number. Of course, of would indicate multiplication in this context. Now, I have parentheses around the phrase verbally above. I did not put parentheses around the math symbols I wrote of 3 minus 2/7 x, but you actually could put them there. It doesn't hurt anything. It just turns out not to be necessary in this example given what's going on. Now when we say the word is, that's going to be our equal sign. Sometimes you'll see a phrase like is equal to or just is. We're going to have just equals here for is. And then we see beyond that 5/7 of that number. So again, there's of for multiplication. So we'll say times or just put the letter x after it, knowing that a number written directly in front of a variable means multiplication. So we now have a total equation of 3 minus 2/7 x equals 5/7 x. Now we want to find the number. Well, this will be in solving the equation using steps we've already done. To get x alone, we'll want to work on variables first, smaller to larger. Now remember, the left side has two terms, one with an x and one without. The right side only has one term with an x. Fine, we can still follow through these steps. To go variables first, smaller to larger, I'm only going to look at the variable terms that involve the x. So we're going to ignore the 3 we see way out at the left side for a second here. Now when I say smaller to larger, remember we want to move the smaller coefficient. Well, with 2/7 being negative, be careful with that minus sign in front of the 2/7, that means negative 2/7, and the right side being a positive 5/7, the negative 2/7 on the left side is actually smaller. So I'm going to move it by adding it or undoing it. So I'm going to add 2/7 x. Of course, I'll have to do that to both sides. So I'll add 2/7 x also to the right side. On the left side, the 2/7 x's, one being negative and one being positive, will cancel out, leaving us only with a 3 over there. And then on the right side, we have 2/7 plus 5/7, which we could add up as 7/7 x. Now, of course, 7/7 as a fraction is really just 1, which means we really have 3 equals 1x, which is another way to say x equals 1, which gives us our final answer for this problem.